So just to give you an outline of what we're going to do, we'll start off by just going over the motivation, how we got into this project. And then we'll move on to the actual project that we worked on, and how we chose to tackle it. Then we'll look at the actual problem that was associated with this project, as well as the experimental data, and then a comparison between our initial prediction and that data. Then we'll look at a root cause analysis that we did to try to further refine the predictions that we made, and then we'll try to boil down some kind of conclusions from everything. So I think it really goes without saying that one of the major goals in this area is always to decrease TSFC. Increasing range and reducing operating costs. That's always a major driver in really behind everything that we do. Now, one of the conventional ways of accomplishing this, at least from a turbo machinery designer's perspective, is we want to increase the turbine inlet temperature. That way we can improve performance of the machine, but this does come at the cost of reducing the durability of the turbine. Now, with conventional designs, the way that we get around this is that we do film cooling. Modern turbines operate at temperatures that are above the melting point of the materials. The only way to do this is to cool the metal pieces with the cold flow coming out of the compressor. Now, the way these cooling systems are generally designed, it's done through empirical processes that are based off of experimental data. And they've worked fairly well, but as we try and push the temperatures higher and higher, that gives less and less margin for error. Very small changes in metal temperature can cause very large changes in the lifespan of the parts. And so these empirical processes, they have a tendency to miss some behaviors as you come up with more and more complicated cooling systems. So really we believe that a more physics-based approach, namely CHT, is probably the way forward. Now on the left-hand side of the screen, what you're seeing is the first vane from an experimental research turbine that the Air Force has put together. Now one of the purposes of this research turbine is to be able to take detailed measurements via blowdown facility of the heat transfer characteristics of the parts. So in order to get a theoretical or CFD prediction, the Air Force supported us through an SBIR contract to develop a high fidelity conjugate heat transfer analysis tool that would be able to predict the performance and the durability characteristics of these film-cooled turbine vanes. Now, we're not just looking at, trying to make a really good prediction for one film hole or characterize, some kind of simplified geometry. What we're doing here is we're actually simulating the entire thing, all the film holes fully resolved. So this is a big problem that we wanted to tackle, and we tried to break it down into three pieces that we focused on. The first is the numerical procedure. How do you couple the fluid and solid properly so that they can transfer the information effectively? Second really is ease of use. One of the most time-intensive manual labor parts of this is getting a good computational mesh for such a complicated geometry. So we wanted to try and streamline the meshing process as much as possible, automate any of it if we could, and also identify some pitfalls for users to watch out for. And then the third and final aspect of this is we want the simulation to be, as fast as we can make it. These meshes tend to be very large. One approach is just to try to optimize the solver as much as possible, and that's certainly something we've done. But really, the best bang for your buck is parallelization. Breaking the mesh into multiple pieces and having it run on separate CPUs. So here I'm just going to describe the actual airfoil a little bit. Uh, so again, this is a first vane of the HIT, the High Impact Technology Research Turbine from the Air Force Research Laboratories. It has a total of 648 foam cooling holes. Those are mostly on the airfoil surface, but there's also some on the ID and OD platforms. You know, one thing of interest is on the right at the leading edge, you have these shower head holes. They're cylindrical, and they're always pointing towards midspan. So right at midspan, they switch over from pointing radially up to radially down. So right here, you have them kind of pointing right at each other. The rest of the film holes on the airfoil surface are these laid-back fan-shaped holes. And then you have some cylindrical trailing edge holes that eject out the back. Now you can see that there's two coolant cavities, one in front that's supplied by the ID cooling supply, and then one in back that's supplied by the OD coolant supply. If we look on the right-hand side here, we can see some streamlines. And what you can see is, if we look at the OD, you have some flow coming into this front cavity. It feeds into these shower head holes. And then in that area where we had mentioned that the cooling holes are pointing at each other, you get some kind of pileup of cooling flow there that propagates downstream. Similarly for the OD cavity, you see it entering the cavity. There's some kind of recirculatory zone here, but then most of it's exiting out the back. So for the mesh, we chose to go with an unstructured mesh for both the fluid and solid domains. And just to reiterate, all the features on the mesh are fully resolved. There's no modeling of the film holes with source terms or anything like that. To generate the initial mesh, we went with an octree approach for the initial surface mesh. We then smoothed that out and filled the rest of the volume in with a Delaunay triangularization. And then to resolve the boundary layer, we use a prism layer extrusion from the surfaces. In the end, the mesh consists of tetra, pyramid, and prism type elements. And one thing we knew we wanted to do early on was on the fluid-solid interface, we wanted to enforce a one-to-one node match. And the reason for this is that we really wanted to minimize the error associated with interpolation on an arbitrary 3D surface. Now the resulting mesh that we used contains a total of 24 million elements. 14 million of those are in the fluid, and that includes both the internal cavity flow as well as the external aero flow. And then another 10 million elements are in the solid. Now, one thing that we ran into that we didn't quite expect is, when you do these kinds of complicated geometries, you expect some kind of translation errors with the CAD. Maybe the surfaces don't mate up quite properly, or the tolerances give you some issues that you have to clean up later. And that we had fully expected. But what we didn't expect was the difference between manufacturing versus what we call a CFD-ready definition. And so, like one thing that we found was that the manufacturing definition wasn't actually periodic. So we had to fix that. And then something else is that there were a lot of gaps in the geometry that were intended to be filled in by some kind of attachment hardware. Or in another case, there were casting holes that were preventing the film cooling cavities from being properly sealed. So that took a little while to fix all of those things. So those are the kind of things you have to watch out for. So the solver that we actually use to conduct the simulation is our own code Leo. So Leo is a density-based code, and we use the cell vertex finite volume approximation. One of the primary reasons that we went with cell vertex is because of its it's very robust even with highly skewed meshes. We can also support either structured multi-block meshes, and for those we use a multi-grid scheme for convergence acceleration, or we support unstructured meshes, and for that we use a residual propagation scheme for convergence acceleration. And again, for all of these simulations that you'll see here, these are all fully unstructured meshes. We're using a k-omega turbulence model based upon Wilcox's formulation, and it's using a vorticity-based production term. Additionally, we support steady state and time accurate flow simulations, but here all the simulations are steady state. Now for doing the actual conjugate heat transfer, LEO contains an optional heat conduction module that performs the conjugate heat transfer analysis. So there's no need to couple this to an external heat conduction solver. Everything's handled internally. And then, as mentioned previously, for the parallel processing, we've gone with MPitch2 for our message passing interface. Now here we'll talk about the actual coupling procedure that we use for the conjugate heat transfer. So on the left-hand side of the screen here, this is a simple 2D case that we used during the development process. This is the NASA C3X case, if you're familiar with that. And you can see you have the external fluid section, the solid, and then you have these internal fluid pipes that run through the airfoil in red. Now, if we look at the zoom in on the surface, what you'll notice is there's a disparity in the length scales in the mesh. So we have, in terms of near wall normal resolution, you have very small cells on the fluid side, but very large cells on the solid side. And that's just because you really don't need that much resolution on the solid side. So the way that the coupling works is that for each global iteration of the solution, we start off with some new set of fluid properties and metal temperatures at each node in both the fluid and solid domains. Using those new properties, we calculate heat fluxes on the solid side and fluid side. And what we really want here is some kind of average heat flux on this interface node at each point on the interface. So we just take the average of those two that we calculate. Now using that new interface, that new heat flux at the interface, we then, on the solid side, use that to calculate a new wall temperature. Now that wall temperature that we use is now imposed as a boundary condition on the fluid side. And that we iterate on that. And the eventual goal is, since we're running a steady state solution, the temperatures should reach a steady state value, and at some point this Q interface should be the same as both the fluid and solid. They should all be equal, and that's how we know we've reached convergence. So on the left-hand side of the screen here, we're just showing the way that we broke up the mesh. It's actually 7 pieces, but due to the color scheme, it's a little hard to see. So we just broke it up in the axial direction. But for the solid piece, we leave this as just one big piece. And the reason for that is that even though they're, if you recall, they're roughly, the fluid and solid pieces have roughly the same number of elements. The solid piece is only solving one linear equation, whereas the fluid pieces are solving 7 nonlinear equations. So even though this is broken up and this is much larger, this solid piece ends up running much faster than the fluid piece. So there's really no reason to break up the solid. Now on the right-hand side of the screen, what we're showing is some convergence histories from a simulation. First, you see the mass flow rate, followed by total temperature and total pressure. If we go back to mass flow rate, what you're seeing here is in blue, we have the inlet flow, and in red, we have the outlet flow. Now, for a normal simulation, you would expect these two lines to join up together if we're satisfying mass conservation. But you have to remember that we're injecting cooling flow into the domain. So there's going to be some imbalance. And for this configuration, we expected somewhere around 6.5% cooling flow, and that's roughly what you're seeing here. So we were pretty happy that we at least got a reasonable answer for first try. Now looking at total temperature, I'm just going to start off. You see the temperatures coming from some very low value before it reaches a steady state. And what's important to note here is that there's really two ways that you can initialize this kind of problem. You can either start off with all fluid is cold at the coolant temperature, or all the fluid's hot. Now, if you start off with hot fluid or core fluid temperature fluid, the problem that you run into is now you have coolant, cooling cavities that are full of hot fluid. Now the Mach number in the cooling cavities is very low, so it takes a long time for that hot fluid in the cooling cavities to get pushed out. If you initialize with a cold fluid, now those coolant cavities start off at roughly the temperature that they're going to end up at, and the core flow region has a relatively high Mach number, so that cold fluid is pushed out of the core flow region relatively quickly. So the lesson to learn here is that initializing to the coolant temperature, so that we focus on the coolant cavities or the low Mach number regions, that gives you a much faster convergence rate than the hot type of initialization. And again, as we saw in the mass flow rate, the temperatures don't quite line up, and that's because of the injection of coolant flow. Finally, if we look at the total pressure, there's really three main sources that are accounting for the drop in total pressure here. There's the normal viscous loss, just from normal interaction between the airfoil surface and the fluid. But there's also, as the coolant flow is injected out of the airfoil, you have some loss due to the jet and cross flow viscous loss. And finally, you have a pretty significant amount of loss just due to pushing all that cooling flow out through these very tiny film holes. So we ran for the simulation for a total of 20,000 iterations to ensure that it was converged. And again, the total mesh count was about 24 million elements. And we ran this on just a regular desktop PC with a total of 8 cores, and it took about 120 hours. So these are the initial results that we got. And they're arranged kind of in an order of the least global effect to largest global effect, and I'll explain that as we go on. So if we look at the pressure, you can see that it mostly varies smoothly as you move along the airfoil. There's some local effects if you really zoom in due to the film cooling holes. But really, this doesn't look too different from if you just had a turbine vane with no film cooling holes on it. As we move over to the skin friction, again, mostly this is a smooth transition, but now you can start to see some kind of wiggles in the contours due to the effects of the film cooling holes. But still, you could imagine this being an uncooled vane. But now as we move to the temperature distribution, you really start to see that signature of the film cooling holes, except it's kind of smeared out. That's due to the conduction effect of the metal. But yeah, you can definitely see the low temperature regions as the film cooling builds up. Finally, we can move over to the heat flux, and here you don't have to really worry about the conduction because the way it works, and you can really see very clearly the signatures of individual film cooling holes. Especially if you look at the shower head region, you can see these little trails or tails as the flow attaches to the surface and then moves away. Now there's really two interesting phenomenon to look at on this heat flux plot. One is, if you recall earlier when we were looking at the streamlines, where those shower head holes point at each other, there was a buildup of cooling fluid. And you can see that pretty clearly on the heat flux along the center here. You see this large region of lower heat flux that builds up. The other thing of interest is you can see the stagnation line pretty clearly in the middle of this shower head region. There's kind of a distinct red line running through here, as well as if you look at the tails from these shower head holes, you can see on either side of that red line they're pointing in opposite directions. So now we have some kind of some kind of prediction, and again, like I said before, the whole reason we got into this was because the Air Force had built this big blowdown facility, and they wanted to be able to measure the heat transfer characteristics of this experimental research turbine that they had built. And so what you're seeing here is this is the ring for the first vane, and there's a bunch of different experimental configurations that they have here. Some are instrumented, some are not, some are cooled, some are not. But these green ones are really what we're interested in. These are instrumented cooled vanes. And you can see an example of one of these on the right here. So what you're seeing is a vane with a heat flux gauge on top of it. This gold part, these are actually the leads, and then you have these little thermocouples or heat flux gauges up here. Then this brown piece is some kind of insulating layer, and then there's another one of these gold heat flux gauges beneath that. Now on the bottom left hand here, this is really just showing the useful time from the blowdown facility. So they turn on some kind of cooling flow, let it cool down for a few seconds, and then they open up this big tank and let the main hot flow come in. And that happens around 6.5 seconds here. Then it runs for roughly 3 seconds, and then the cooling flow is turned off. So you can get roughly 3 seconds of data. On the right-hand side here, we're just showing some sample data that's taken at a given run and location. And the important thing to see here is, we have data for both the top and bottom heat flux gauges. And so the way that we're going to actually calculate the heat flux is that, we take the difference of these two readings. And since we know the material properties and thickness of this insulating layer, we can then use that to calculate the heat flux across this. Now here's a sample of the actual experimental data. And so the way to look at this is 0, and this is going to be true for all of everything we see from now on. At 0, this is the leading edge location. As we move towards the left, towards -1, we're moving along the pressure side to the suction side, to the trailing edge of the airfoil. And as we move from 0 to +1, we're moving along the suction side of the airfoil towards the trailing edge. So 0 to -1 is pressure side, 0 to +1 is suction side. So on the left-hand side of the screen here, you can see the surface temperature for the 5 and 62% span. And on the right-hand side here, you can see the surface heat flux for 5 and 62% span. Again, the surface temperature, that comes from the top heat flux gauge, the one that's sitting on top of that insulating layer. And then the heat flux comes from the difference between those two. So there's data acquired at 6 different span-wise locations. In this presentation, we're mostly just going to focus on the 62% span, just to keep things simple. But one thing to note that I forgot to mention is for any given experimental run, only 2 span-wise locations could be measured due to limitations on the number of data channels. Okay, so here we have our first result compared against data. So the way that we actually took these blue curves, the CHD prediction, is kind of neat. There's a we found a tool in TechPlot that actually lets you project a line onto the surface and extract data from that unstructured surface mesh. So it's actually diving in and out of the film cooling holes. So what we see here is that the heat flux it shows a lot of oscillation and a very jagged behavior. Um, it's kind of hard to say, is this right or not. It kind of looks like it maybe the data is okay, but there's such a large spread in the prediction, it's really tough to say. When we look at the temperature, however, especially looking at the pressure side here, we're under predicting quite a bit. The suction side looks okay, uh, but in this case, since the pressure side is so poorly predicted, it's hard to say if this is actually correct, or maybe it's just dumb luck that it's falling in the right place. So this result was a little disappointing for us, and we decided to really try to investigate what the heck was going on here. So we decided to instigate a root cause analysis. So there's really 5 places where you want to look for where these problems could be coming from. The first is the geometry. Are we sure that we're simulating the right airfoil? So we really tried to spend a lot of time looking for any kind of discrepancies between what was designed, manufactured, and what we actually simulated. And we found some minor differences, but really nothing that caused the kind of difference that you saw in that last plot. Uh, the next step was to look at, are there any limitations of the solver that could be causing such a big disagreement? And we found one minor thing in the way that the wall functions were formulated, but really all that did was to uh, tie up the difference between any kind of wall integration and wall function solutions. But really that didn't answer any questions about why we were seeing such a big difference between the experimental data and the prediction. Finally, or not finally, sorry. The next step was, are we misinterpreting the data at all? Could the instruments be at a different location than we think they are? Are there any kind of interference effects that we're not taking account of? And we didn't really find anything here. But these last two, the boundary conditions and the critical features not modeled, these turned out to be big ones. I mean, for boundary conditions, you could have some kind of idealized solver, but if you put wrong boundary conditions into it, you're going to get garbage results out. And similarly, if there's something important going on in the experiment that you're just ignoring for whatever reason, it's going to be very difficult to capture the correct results. So more on this critical feature. We had mentioned earlier that in the heat flux gauges, there's this brown insulating layer that's called kapton. Now, we had thought we had wanted to simulate this right from the beginning, but the technology really wasn't there to do it properly. So after we saw this result, we developed some technology just so we could answer the question, we have this there in order to take measurements, but is it actually influencing the results as well, or is it thin enough that it doesn't matter? I mean, the Kapton has a very low heat conductivity. The difference between the metal and this insulating layer is something like 2 orders of magnitude. So even though it's only something like 50 microns thick, it was definitely a concern that this could somehow be influencing the solution. And so after we developed the new technology to implement this, we got this solution. And just looking at the heat flux, on the left-hand side, we have the old bare metal solutions. And on the right-hand side, we have these new solutions with this Kapton layer implemented. And looking at the heat flux, you can see much larger areas of green. The heat flux has gone down quite a bit. Now, one thing I'll mention is looking at these contour plots. The difference is actually larger than it seems. These contour plots have been clipped in a way that emphasizes the signatures of the film cooling holes, but you'll see line plots that show this a little bit better later on. Looking at the metal temperature, again, we see the temperature everywhere on the airfoil has increased. You can see much smaller regions of blue on the pressure side here, and even the attachments have gone up in temperature. So the temperature has gone pretty much up everywhere on the airfoil due to this inclusion of kind of like wrapping a winter coat around the airfoil. So again, here we have plots of the data versus the CFD prediction. And the first thing that you see looking at heat flux is there's just a large decrease in that jagged behavior, at least in the amplitude of it. And again, it still seems to be matching up well with the data, but the amplitude of these oscillations now seems a little bit more believable given the position of the data. Looking at the temperature, though, so originally, one thing I forgot to mention, red is the new prediction with Kapton. Blue is our original prediction. So if you look at this our blue original prediction, you could see that on the pressure side we were pretty severely under predicting here. Now with the addition of the Kapton, the temperature's gone up everywhere, so it's still not quite right, but now this is looking more reasonable. However, now when we look at the suction side, now it's very much over predicted on the suction side. So heat flux is looking better, but in terms of temperature, it's kind of a one step forward, one step back kind of situation. So clearly there's something else that we're missing that's going on here. So the next step was to work with the Air Force again, and after a lot of collaboration, they helped us to realize that we were using the wrong boundary conditions. What was happening is, if you remember that rainbow wheel, there's a lot of variation in the coolant flow conditions as you move around the wheel. It's not just uniform. So they helped us to they provided us a lot of data, and they helped us to figure out the conditions for the localized conditions for the airfoils that we were simulating. So if you look at the bottom here, you can see the results of that analysis with the old versus the updated boundary conditions. So if we look at the ID conditions, first you can see the temperature ratio has gone down a bit, as well as the pressure ratio for that ID cavity has been increased a little bit. For the OD supply pressure or supply temperature, that was pretty much correct. But when you look at the supply pressure for that OD cavity, it's decreased very significantly. Now, when we look at the effect of this, so on the left-hand side here, we have bar charts showing the supply pressure before and after we did this. So again, the ID cavity saw a bump up in pressure, so you'd expect to see some more coolant flow coming out of there, and the OD cavity saw a large decrease in pressure, so you'd expect to see a significant decrease in flow. And that's exactly what we see. The ID cavity, when we look at the cooling flow rate, it shows an increase in flow, and the OD shows a decrease. Now, when we look at the before we go into this, it's important to note, where does the ID have influence and where does the OD have influence? So on this chart, the ID flow cavity, it's supplying cooling air to maybe like half of the pressure side and the entire suction side. So that ends roughly here, is where its influence ends. Everything to the left of this is supplied by the OD cavity. So really, in terms of heat transfer, there's not too much difference. Around midspan, uh, there's an increase in heat flux, but no very large changes. When we look at temperature, however, now we see some pretty significant differences. So from the OD cavity, we saw an increase in cooling flow, and when we look at the temperature, what we see is a decrease in temperature everywhere where that's affected by the ID cavity. Similarly, for the OD flow, we saw a decrease, and we see a corresponding rise in temperature in areas that are influenced by the OD flow. The end result is now the data is, or the predictions are actually starting to make pretty good sense with the data that we're seeing. So now we get to kind of go back and look at this entire progression that we've gone through. So initially we saw, very large fluctuations in the heat flux. There's kind of, the amplitude's so large it's kind of hard to tell, is it actually matching up with the data or not. When we looked at the temperature, however, on the pressure side, there was some severe underprediction, and because of that, the results on the suction side, even though they look fairly good, it's hard to believe them. We then added accounted for the thin insulating layer due to the kapton in the heat flux gauges. And what we saw was those oscillations in the heat flux were decreased pretty significantly, and they're brought into kind of a more believable range given the data that we have. What we saw in the temperature was that, okay, now on the pressure side, the prediction has come up to a more believable value. It's not quite right. We're still under predicting, but it's starting to get in the ballpark. However, when we look at the suction side now we're severely over predicting. And finally, with the help of the Air Force, we reviewed the data on the boundary conditions and came up with a more accurate set. And there wasn't a huge change in the heat flux, but what we saw was that this redistribution of cooling flow, with that redistribution, now we're seeing a much better agreement between the data and the CFD predictions. In conclusion, we ran this conjugate heat transfer simulation for the first vane of the AFRL's high impact technology research turbine, and this thing has a total of 648 film cooling holes. All the film holes were fully resolved using an unstructured mesh, and prism elements were used to resolve the boundary layer. The solver that we used was ADS code Leo, and again we ran a conjugate heat transfer simulation with that. Our initial results, we compared them against the data, and they showed a significant underprediction of the measured temperature. We instigated a root cause analysis, and we discovered two major drivers of the disagreement. First was the kapton layer that's used in the heat flux gauges as the insulating layer, and that showed a strong insulating effect, which results in higher temperatures on the surface as well as lower heat flux. And additionally, we were able to get more faithful boundary conditions that resulted in an improved distribution of the cooling flow, which led to better temperature predictions. Moving forward, we're always looking to exercise the tool against more cases so that we can further validate this conjugate heat transfer process. And additionally, we're definitely looking to develop a methodology for actually integrating this process into a manufacturer's design cycle. So Mike, do you want to take over?
Thanks a lot, Will. That was a great presentation. I'd like to now kick it over to questions. If you have any questions, what you can do is on your GoToMeeting, panel, there is a little hand. If you click on that, you'll raise your hand, and then I will unmute you, and you can ask your question. Please just state your name. when
Bob, do you want to unmute yourself?
well, we don't seem to have any questions. Maybe Bob, if you would like to make comments on the presentation. Um,
Yes. How are you, everyone? This is Ron Ho Ni, and people call me Bob. And what we at AeroDynamic Solutions, with the support from Air Force, have developed this conjugate heat transfer capability. And we spent a lot of time in doing this research. And as you recall, Will mentioned, the calculation initial results did not match data well. And in generally, in the life, was always the case. So we went through a root cause analysis, and this consists of 5 parts: geometry issue, CFD software issue, data issue, boundary condition issue, as well as the critical feature associated with the calculation. We spent a lot of time going through each one of those possible root cause, and then find out 2 driving factors. One is from the boundary condition. The other is from the Kaplan layer. I think this is a very important step we took. For people working on CFD, generally have an intention only look at the turbulence model or grid refinement. If we go in that direction alone, we'll not be able to get to the solution how we have today. So it's really critical to look at this problem from a much broader perspective. Not only look at the CFD code, these people working on CFD require a better understanding of the geometry and how the experiment was conducted. So we are lucky working with Air Force people closely and getting to this point. So it's really important point is that saying in this effort, root cause analysis is critical step of making a good CFD tool a useful tool. All right. Here's my comment. And
thanks, Bob. We actually have a question. Amy Mensch.
Yes. Can you hear me?
Yes.
Yeah. Okay. My name is Amy Mensch. I am from Penn State University. I work with Professor Karen Tolley. And I had a question about the results that you obtained when you added the Kapton tape. On the pressure side, it looks, you mentioned this, that the temperature increased. And I thought that was interesting because you're adding an insulating layer, and intuitively I would think that would mean your temperature would decrease.
Well, this is the temperature on the outside of
this is
top
the external
thermocouple.
temperature.
Yeah. This isn't on the
Okay.
metal surface. This is, the top layer.
Okay. All right, then that answers my question.
Amy?
Thank you, Amy.
Amy, thank you very much for your question. And also, I enjoyed very much your presentation at ASME conference.
Thank you.
Okay, if there are no further questions, let's move on.
Oh, by the way, Amy.
I'd just like to take this time to acknowledge our software partners. We did use TechPlot 360 for our 3D visualization and streamlined plots. Also, the unstructured mesh was generated using ISOM, and alternately, we have used Pointwise to also generate the unstructured film-cooled mesh. Both papers, all the information that you have just been so eloquently exposed to by Will is available online at www.aerodynamicsolutions.com/help/downloads. We also have various other case studies there for you to take a look. Why don't you go to the next page?